This is the 15th video in our series on topology, and in the previous video we looked at the very basic definitions and results regarding compact sets. And today we want to look at a couple of more examples and a couple more general results. Let's first recall our definition of compactness. Now, this isn't the full definition we wrote last time, but it captures everything that we need to remember. So we say that X is compact if every open cover U of X has a finite subcover. Recall that an open cover was a collection of open sets that union to the whole space. And well, a finite subcover is simply a finite subcollection of that collection. Okay, so now let's look at some examples and non-examples that we said last time, or that we looked at last time. The closed interval from 0 to 1 is compact. The open interval from 0 to 1 is not compact. This reciprocal of all natural numbers, well, the set made of those, is not compact. But if you add in 0, you do get something that's compact. So if you didn't watch the previous video and you want to see how we did those proofs, make sure and go watch the previous video. Now, I want to start with the example of the real line with the lower limit topology. Recall our notation for that is R sub L. And let's also recall that inside of this lower limit topology, the open sets are the so-called normal open sets, the ones that are open in the Euclidean topology, along with these intervals that are maybe open on the right-hand side but closed on the left-hand side. See, so these half-open intervals. That's why it's called the lower limit topology. It contains the lower limit point. Okay, so now we want to look at the following question, which is, can we somehow classify the compact subsets of R sub L? And you'll see that we will be able to. Okay, so let's say that we've got a non-empty compact set, and then let's take some sort of X in K. So we know it's non-empty, so we can take a point from K, and then from this X, I want to build an open cover. So I'll just say that here, I'm going to build an open cover. And what's that open cover going to look like? Well, it's going to be made of two flavors of sets. The first set will go from minus infinity up to X minus 1 over n, and it'll be an open interval. And this ranges over all natural numbers. And then the second flavor of open set in this open cover will simply be the interval starting at X, including X, and going to infinity. So let's observe that this open interval is open because our lower limit topology has the quote-unquote normal open sets as open sets. Whereas this half-open interval is open in the lower limit topology by our construction of the lower limit topology. Okay, great. So now, since we've got an open cover of our set K, what I want to do now is take a finite subcover. So let's say we're going to do that. So let's take a finite subcover. I guess maybe we should talk a little bit about how we know that this covers K before we go on. But let's notice that this set, or this collection of subsets here, actually covers all of RL. If you take this limit as n goes to infinity, notice that you'll get the open interval from minus infinity up to X. And that's going to glue together with that interval that's open in our topology to build all of X, or sorry, all of R. So anyway, that's why it covers it. We previously talked about why it was an open cover. And then again, since K is compact, we can take a finite subcover. And so notice that our finite subcover will have one of the following forms. It'll have finitely many things from here only, or it'll have finitely many things from here along with this set over here. So let's write those down. So it's going to be of the form minus infinity X minus n sub 1 union minus infinity up to X minus n sub 2 union dot 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 up to minus infinity comma X minus 1 over n sub K. Okay, so that's taking finitely many things from this first bit. And then we may or may not have to take something from this second bit, but there's only one set in the second bit. But now that we look at it a little bit closer, we do need this second set. And we know that we need the second set because none of these first things contain x, but we know that x is in k, and if we're trying to make a finite subcover of k, well, our finite subcover has to contain x, and this one contains x. Okay, so anyway, it being a finite subcover means k is a subset of that union. But now I'd like to observe that these intervals minus infinity up to x minus 1 over n are all nested. So when we take their union, we simply get the biggest one. And what's the biggest one? Well, notice that the biggest one is going to be whichever one has the smallest number subtracted from x. But in order to subtract the smallest number from x, we need the largest denominator. So there's a bit of a game there with smallest, largest, smallest, largest. But in the end, we can write this union as minus infinity up to x minus 1 over n. And then we've got that unioned with x to infinity. And then, well, since this capital N here depends on x, I'm going to put an n sub x right there. Okay, good. But now let's note the following, and I think this is probably pretty clear, and that is if we take, but let's notice since k is distributed between this interval right here, minus infinity, up to x minus 1 over n sub x, and this interval right here from x to infinity, that means that k will not intersect with the really little bit there that's left out. So let's write that here. We have k intersected with this interval starting at x minus 1 over n sub x and ending at x, including the lower limit but not the upper limit. So this intersection is empty. And again, just to be really careful, that's because this interval right here fits exactly in between these two pieces, which we have argued contain k. Okay, good. So now what we want to do is maybe choose, I guess we're using a choice function here, which means we're really using the axiom of choice, but we're not going to be super careful with that. So now what we want to choose is a rational number from this interval. So I'll call that rational number q sub x. And well, like I said, it needs to be from this interval, x minus 1 over n sub x, all the way up to x. And just to show that it's rational, I'll say that that is being intersected with the rational numbers. Okay, so now what are we going to do? So now let's define a function q starting at k and ending at the rational numbers. And how is it defined? Well, if we evaluate q at x, we're going to simply get q sub x. So that might seem like kind of strange, but what's going on here? Well, up here, we take our x from k, build an open cover, and then go through this argument right here to choose that rational number. But we're going to take that entire process to be the development of our function going from our compact set to the set of rational numbers. But now I'd like to note that in this case, q is actually injective. And we can see that q is injective because if q sub x, which is equal to q of x, is equal to q of y, which is equal to q sub y, then what does that tell us? Well, that tells us that q sub y comes from the interval from x minus 1 over n sub x up to x. But then it also comes from the interval defined off of the y. So let's say that's y minus 1 over n sub y up to y. But then the choice that we had only took exactly one rational number from every interval that looks like this. But since we chose this same rational number from those seemingly looking two intervals, then that means that those two intervals must be the same. But then if those two intervals must be the same, that means that x must in fact be equal to y. But look, that shows that this function q down here is injective. So what have we done here? Well, we found a one-to-one map from k to the rational numbers. But that means that the size of k, or the cardinality of k, is at most the same as the cardinality of the rational numbers. In other words, k is either finite or countable. But I'll just put right here by saying that k is countable. And just we'll include finite in our definition of countable, which some authors do. So I think this is a pretty interesting result, because what have we seen? We've seen that the only compact subsets of the real line with the lower limit topology are countable. And so that excludes like most of the so-called normal subsets that we work with, or the normal subsets of the real line at least that we work with. Okay, so now let's move on. Okay, so hopefully you've noticed that throughout the course of these videos, we've introduced a topological concept, and then generally we've shown that those topological concepts often are transferred through continuous functions from the domain to the codomain, and that's what we're going to show here. So let's suppose we've got a continuous function from x to y, we'll call it f. Let's also suppose that x is compact. And then we want to prove that the image of f of x, is also compact. Okay, so how can we do that? Well, I'll call this script v, be an open cover of our image f of x. So that means there's a bunch of open sets inside of v. They're open in Y or open in the subspace topology if you really want, but we can just take them to be open in Y. And then if we union them, their union will contain the set f of x. Okay, great. And now let's consider the collection of open sets inside of x, which are simply the pre-image of all of these open sets from V. So in other words, this is going to be the pre-image of V, as V runs through everything from this fancy script V. Okay, good. And now I'd like to notice two things, and I think they're pretty straightforward to notice, but we will sketch why they are true. So notice that U is a collection of open sets, and that's simply because F is continuous. And the pre-image of an open set is open for a continuous function. That's our topological definition of continuity. So now moving on to the next thing, we also need to observe that U covers X. Now, how can we show that? Well, this is pretty straightforward as well. Let's take a little x in big X. But notice that that means that f of x is inside of the image f of capital X. But that means that there exists a v sub x inside of our script v, such that f of x is inside of v sub x. But then that means that x is inside of the pre-image of v sub x. But that pre-image of v sub x is pretty clearly by definition in U. Okay, great. But then that means the following, that capital X is equal to the union over all x in X of the pre-image of v sub x. Now, this is not a union of everything inside of our script U, but it's definitely a union of a subset of things in our script U, meaning that this is a subset of the union over all U in U. But anyway, that just means that we have shown that U covers X. Okay, good. But now, since X is compact, that means that we can find a finite subcover. So let's see, there exists a pre-image of V1 all the way up to a pre-image of Vn inside of U, such that we have x equals the pre-image of v1 unioned all the way up to the pre-image of vn. So we took our finite subcover. It just turns out that the elements of our cover U are of this weird form. They're pre-images of things inside of V, but that's really not a huge deal. Okay, so now we'll apply F to this formula right here, and we'll see that F of X, the image of our function F, is simply equal to V1 union all the way up to Vn. And in fact, right here, I don't actually get an equality because I think we only get equality if this thing is 1-to-1. We actually get a subset relationship here. But actually, the subset relationship thing is the only thing that we need here because what we've shown is that we've got an open cover, or if we have an open cover, we can construct a finite subcover. But that's exactly what we've done. Okay, so now let's move on. For our next result, we'll say that we've got a continuous bijection from x to y. Let's also suppose that x is compact and y is Hausdorff. Then under those assumptions, we actually have that f is a homeomorphism. Let's recall that a homeomorphism is a continuous bijection where the inverse map is also continuous. So sometimes that's called a bicontinuous bijection. But anyway, the only thing that's left off of this is that the inverse map, f inverse, is continuous. But notice that that means that if u in x is open, we need to show that f of u, the image of u in y, is open. Okay, so let's get to that. So let's suppose that u is an open subset of x. But notice if it's an open subset of x, then its complement, x minus u, is closed. That's by the definition or the duality of closed and open sets. Okay, so now we're going to use some results either from last time or just a few minutes ago. So by the last video, we proved what? Well, we proved that A is compact. And well, exactly how do we know A is compact? Well, what we proved is that if you have a closed subset of a compact set, that's necessarily compact. But since A is closed and X is compact, that means that A is compact. Okay, good. But then, since we've got a continuous function, that means that the image of A is also compact. Okay, cool. And then by last time, again, this actually tells us that f of A is closed. And exactly what was that? Well, last time we proved that if we had a compact subset of a Hausdorff space, then that set was closed. And that's exactly what we have here. We've got a compact subset, f of A, of a Hausdorff space, y. So that means that f of A is closed. But now we're pretty much done because notice that f of u is going to be the same thing as f of x minus A, which is going to be y minus f of A. But that's going to be the complement of a closed set, which is an open set. But notice like starting here and ending here was exactly what we said we needed to show to prove this result. Now we're going to prove a really important lemma for our next big result called the tube lemma. So it might seem kind of technical, but in fact you'll see why it'll be so useful for our next result, which has to do with the product of compact spaces being compact. So let's say we've got a topological space X and we have a compact space Y. Let's also say that we've got an element little x from big X. And then if N is an open subset of the product X cross Y, so that this singleton containing little x cross Y is a subset of N, then there exists an open set W of X where little x is inside of W and W cross Y is a subset of N. Okay, so let's look at what's going on here. So over there, I've got my little slice, if you will, this singleton X cross Y. So here, let's underline that in yellow to show that that is that space over there. And then, well, what's this N? So this N is an open set that contains this X cross Y. So perhaps the N might look something like this. So maybe it kind of flares out like that. Okay, and then maybe we would shade everything in like this. So this thing is like our set N. Okay, so that's what we're assuming is our setup. And now let's look at the result. So the result says that there exists an open set W that contains little x. And so that open set W containing little x, we can kind of draw like an open interval down here on the so-called x-axis, although we want to think about it like a more general open set. And then we know that W cross Y is a subset of N. So that means that if we throw these vertical line segments up, that's totally contained within N. So that's the picture of the scenario. Now, a priori, we don't know that that's always possible. That's what we're trying to prove. Okay, so let's get to it. So let's observe the first thing, and that is our space Y is homeomorphic to the singleton little x cross Y. I think that's pretty clear, but maybe our map we would take would just take Y and send it to the ordered pair XY. But now, since Y is compact, and we've got that homeomorphism, that means this singleton X cross Y is also compact. Well, it's a continuous image of a compact space, so it's got to be compact. Okay, so next up, let's take an open cover of this set. So let's say that open cover, is built from things that look like this. So we're not going to take an arbitrary open cover. We're going to take a special open cover and then use compactness to take a finite subcover. So our open cover looks like this. So it's going to look like UI cross VI, which are subsets of N, and UI is in X, which is open, and VI is in Y, which is open. And then I guess we should say our I comes from some indexing set I. So I'm careful to say it's an indexing set I because it might be some sort of uncountable indexing set. Okay, so next up what we want to do is find a finite subcover, which is possible because we're within a compact set, and rename, if we have to, so that we have maybe simple naming scheme for this finite subcover. So let's write it down as X cross Y is a subset of U1 cross V1 unioned all the way up to UN cross VN. So that's the renaming of the sets as necessary to make them kind of look nice. And now let's, without loss of generality, assume that our point X is inside of UI for all I from 1 to N. Now you might say, well, how can we do that? Well, otherwise, so let's say, well, what happens if X was not in one of those? So if X was not in one of those, let's say the jth one, then UJ cross VJ intersected with our X cross Y would be empty. But that's kind of boring because notice that UJ cross VJ would be one of the sets from our open cover. And if it doesn't intersect the thing that we're trying to cover, then we don't need it. So we might as well only keep the ones that contain this point X because otherwise, again, we don't need them. Okay, but now if we've got X is inside of all of those, then that means that X is inside of their intersection. So let's call their intersection W. So let's say W is the intersection of U1 up to UN, and that contains X. So check it out. We've just created a W containing X. And now we need to show that W cross Y is contained inside of N. And we can finish that off with the following claim. And that is that W cross Y is not only a subset of N, but it's a subset of this union right here. So let's write that down. So U1 cross V1 unioned all the way up to UN cross VN. But then why will that be a subset of N? Well, all of that will be a subset of N because of our choice right here that this UI cross VI was a subset of N. Okay, so let's see how that might go. And it's actually pretty straightforward just by following elements through. So let's suppose that we've got a point here, and maybe we'll call it WY, and that's because the little w is going to come from the big W, and the y is going to come from the y. Okay, so well, what does that tell us? That tells us that there exists some sort of I where x comma y is inside of ui cross vi. So we know that's true by this step right here. So we know that x comma y comes from this. This is a subset of this union, so there's one of the pieces of that union that contains our x comma y. And then let's also note that our w is inside of w, right, from this right here, but that means that w is inside of ui for all I, just based off of how we found this w right here. Okay, so let's see what we've done. We took this w comma y inside of w cross y. We showed that x comma y was in ui cross vi, but that means that this y is in this vi. But then this w is going to be inside of all wi. But then if w is in all of the wi, and then y is in one of the at least special vi's, that means that w comma y is in, well, that special ui cross vi. But then that means that it's got to be inside of this union right here. But then again, by our construction of our open cover, that's going to be inside of our set N. So, well, we've done it. We've constructed this W satisfying the conditions that we want it to satisfy. Okay, so now let's see how we can use this. Okay, so now for the big result of the day. So we'll show that if x and y are compact, then x cross y is also compact. Okay, so let's suppose that this script U is an open cover of x cross y, and we pretty clearly want to find a finite subcover. Okay, so now we're going to use that previous lemma, otherwise we wouldn't have proven that previous lemma. So let's fix an x in capital X and consider that slice that we were looking at previously. So that would be the singleton x cross y. And well, just to point out that that is a subset of our product space x cross y. And now let's notice that this singleton x cross y is compact, just like it was in our previous theorem. We can use the same argument for that as well. Let's also notice that since U covers all of x cross y, it most definitely covers this singleton x cross y. But then we've got an open cover of a compact set, but that means we can find a finite subcover. So let's find a U1 up to UN such that our singleton x cross y is contained in this U1 unioned up to UN. And I guess I should say that these all come from our open cover. Again, that's because we had that compact space there, and well, since it covered the bigger space, it's going to cover the smaller space, I think, pretty clearly. Okay, nice. And then, well, I'm going to also note that this U1 up to UN depend on this choice of x here. So since it depends on the choice of x that we're making right here, I'm going to decorate these with a superscript of x, just to show that these sets that we're choosing right here are going to depend on that little x that we chose from. So that means we've got this u1x up to unx. But now let's observe the following. We can think about this u1x unioned up to unx as an n sub x. So it's an open set containing this singleton x cross y. But notice that we can apply our previous lemma to this setup, because this is exactly the setup of our previous lemma, that thing that we called the tube lemma. And so that means that there exists an open set W of x that contains x. That was important that this open set contained x. Again, it was an open set of x such that we have W sub x cross y is contained inside of n sub x. So let's kind of take a breath and see what we've done. Okay, so let's see what we've done here. So for each x in x, we've constructed this open set W sub x of x, where little x is in W sub x, and W sub x cross y is a subset of n sub x. And furthermore, this n sub x was this union right here, this u1 upper x unioned all the way up to un upper x. Okay, so kind of a lot's going on here, but I think it's not too bad. So now let's note the following, and that is that x equals the union over all x in x of W sub x. I think that's pretty clear, right? So this W sub x contains x, so definitely everything from capital X is contained in this. And then the containment goes the other way as well, because these are all open sets of X. But what does that tell us? Well, that tells us this collection, W sub X, as X ranges over all capital X, is an open cover of our X, our topological space X, which we are assuming to be compact. But that means that there exists, well, a finite subcover, because X is compact. So I'll do some renaming and call that W sub 1 up to W sub m inside of this collection. Maybe let's give that a name. Let's maybe call it this kind of script W here. So inside of this script W, such that X is equal to W sub 1 unioned all the way up to W sub m. And now, finally, we're ready to go. So let's see how we can finish everything off. So let's notice that x cross y is going to be equal to W sub 1 cross y unioned W sub 2 cross y union all the way up to W sub m cross y. So, well, that's because x is the union of all of those w's, and then, well, we're just crossing everything there with y. So I think we're good to go on that point of view. Good. But now let's also notice that for each of these w's, the w cross y is inside of this thing that we called n sub x. But this n sub x was this union of these u's here. But that means that we can replace all of these, this W1 cross Y, this W2 cross Y, this WM cross Y, with this thing right here. And, well, we really get something that looks like a subset relationship because of this, but since we're starting at the biggest possible space, it's going to be set equality. So let's see, in the end we're going to have something like this. So this is going to be U1 upper 1 unioned up to UN1 upper 1. And then that's going to be unioned with U1 upper 2 unioned up to UN sub 2 upper 2. And then all of that is going to be unioned up to U1 upper m unioned all the way up to UN sub m upper m, where I needed to change this ending index depending on kind of what W we were part of. But the important thing here is, even though we've kind of multiplied the number of elements of our finite subcover we need, we still do have a finite subcover. And each of these U sets does come from our script U originally. So we had our open cover and we were able to construct this, well, it looks rather large, but this large finite subcover. But that means that our X cross Y is compact. So let's look at a quick application of this result. All right, so our first application is the following corollary. We just showed that the product of two compact spaces was compact. Well, inductively, that really shows that the product of finitely many compact topological spaces is also compact. Now, here's another quick application, and we'll be able to prove this result really quickly in the next video. But with the technology that we have right now, I think this is the best way to do it. So I want to show that the closed disk is compact. So that's going to be all xy, where x squared plus y squared is less than or equal to 1, inside of R2 with the Euclidean topology. Okay, so how can we do this? So previously we showed that the interval from 0 to 1, the closed interval from 0 to 1 is compact. But then that means the closed interval from -1 to 1 is also compact. And that's because, well, that's homeomorphic to the closed interval from 0 to 1. In fact, any closed interval a to b is compact with the same argument. But that means if you take the product of -1 to 1 with itself, you get something that's compact. So that might be -1 to 1 squared is compact. So now let's draw a picture of that over here. So -1 squared would be something like this. Okay, but now let's observe that our set D is a closed subset of a compact set. But that means that it's compact. So that means that D is compact. Okay, cool. Now I want to finish this video with a bit of like a homework problem type result. And that result says that if we've got a topological space X, and Y is a compact Hausdorff space, then F is a function from X to Y is continuous if and only if the graph of F is a closed subset of X cross Y. Now, what's the graph of F? Well, it's all ordered pairs X comma F of X as X runs through all X. So I guess we could draw a little picture of that over here. So let's say this is X and this is Y. So a nice picture of the graph of X might look something like this. Okay, cool. So if you look at that, that's kind of like clearly closed looking, but you will see that we'll use compactness in one direction and Hausdorffness in the other direction. Okay, so let's do this forward direction first. So let's suppose that F is a continuous map. And then, well, what do we want to do here? So let's also suppose that we've got an ordered pair x, y, and it's not inside of the graph. So if it's not inside of the graph, then it's going to be inside of the complement of the graph. So x cross y minus g of f. So if we can show that the complement is open, then the graph is closed, kind of by definition of open and closed. Okay. But notice that that means immediately that y is not equal to f of x. Because if y was equal to f of x inside of this ordered pair, that means that this ordered pair would be on the graph, but we've just assumed that it's not on the graph. But then both of these are inside of y, which is Hausdorff. And now this is an important thing. We've got 2 points that are not equal. So in other words, we've got 2 distinct points inside of a Hausdorff space. So what does that mean? So that means that we can find something that I'll call U and V, which are open subsets of Y, such that maybe Y is inside of U, and maybe f of x is inside of V, and we know that U intersect V is empty. Okay, anyway, we just applied the property of Y being Hausdorff. Okay, nice. Then let's also note that we know that the pre-image of V is an open set. And that's because we've got a continuous function. So let's see what we've used so far. We've used the continuity of the function, and we've used the fact that y is Hausdorff. Okay, then let's also note where is x. So x is going to be in the pre-image of V just because f of x is in V. I think that's pretty clear. So we've got an open set containing x now. But now putting some of this stuff together, what do we have? Well, we're going to have x comma y is inside of the pre-image of V cross U, like by our construction of all of these sets. And so that leads us to want to show that this pre-image of V cross U is contained in our complement of the graph. And if we can show that it's contained within the complement of the graph, then what have we done? Well, we took an element in the complement and we found a neighborhood of that element that's contained in the complement. In other words, we've shown that complement is an open set. Now, let's suppose that we've got something that's inside of this, but it's also inside of G of F, or sorry, G sub F. So in other words, this is not contained in the complement. And we want to show that something goes wrong there. So let's suppose that Z comma F of Z is inside of the pre-image of V cross U intersected with G sub F. But that tells us that F of Z is inside of U and Z is inside of the pre-image of V. That's just because this ordered pair is inside of this cross product right here. Notice this ordered pair kind of by definition is inside of that graph. Over there, we didn't really need to write the intersection with the graph due to this format of our ordered pair, but we did just, I don't know, for some flourish. Okay, but now check it out. If we apply F to this thing right here, we have F of Z is inside of V. But notice that F of Z is inside of U intersect V, which we said was empty. Of course, you can't have anything in an empty set, so that means that such a point right here cannot exist. But if such a point right here cannot exist, that means that this intersection right here is empty, but that intersection right there being empty is precisely us having an open neighborhood contained in that complement, which again finishes off the proof that this complement is open and thus the graph is closed. Okay, so that's the forward direction. Now let's look at the reverse direction. Okay, so now for the reverse direction, let's start by supposing that the graph is closed and we have an open subset V of Y. Now we want to show that the pre-image of V is open. That's what it would take for F to be continuous. Now, I want to start by saying, without loss of generality, let's assume that the pre-image of V is a non-empty set. Because if the pre-image of V is the empty set, then it's already open and we haven't really done anything. Okay, but then if the pre-image of V is non-empty, then that means there exists some point which we'll call x naught inside of the pre-image of V. But if x naught is inside of the pre-image of V, that means that f of x naught is inside of V by definition of the pre-image. Okay, so now what are we going to do? Well, now let's notice that G sub f intersected with x cross y minus V is a closed set. So let's look carefully at why that's closed. Well, we're assuming that G sub f is closed. And then, well, this y minus V is closed because it's the complement of open. And then we're crossing it with a closed set, so that means that's also closed. So we've got the intersection of two closed sets, which we know is closed. Okay, and now we're going to use something called a projection map. So let's maybe recall the definition of that real quick. So let's say we've got this projection map, which I'll call pi1, and it takes x cross y to x, and it's defined, well, exactly the way you might think a projection map is. It kind of forgets anything having to do with y. So it takes pi1 of an ordered pair xy and simply sends it to x. So of course that's not the claim, that's just the definition of the projection map. So what we'll show is that if we have the projection map, then if we apply pi1 to g sub f intersected with x cross y minus v, we're going to in fact get x cross the pre-image of v. Okay, nice. And well, this is not actually that bad of an argument. We can just do it by chasing some elements around. Okay, nice. So let's suppose that x is inside of pi1 of, I'll just put a line here to mean all of this stuff. But what does that tell us? Well, that's equivalent to saying that x comma f of x is inside of x cross y minus v. And that's because this x coordinate came from something in the graph. So that means the y coordinate that this x came from must be of the form f of x. So the fact that we've got an f of x over here comes from the fact that we started at the graph. Then the fact that we're in x cross v minus y comes from the fact that we started inside of this intersection. Okay, now that's going to be equivalent to saying that f of x is inside of y minus v. Now, why is that? Well, that's because any of these little x's over here is in capital X. That's not really adding in any information. So the only information added by that being inside of the x cross y minus v is f of x being inside of y minus v. But notice that's exactly the same thing as saying that x is inside of the pre-image of this over here. But the pre-image distributes across set minus, and that'll simply leave us with x minus the pre-image of v, because the pre-image of y is most definitely going to be x. But now, how does that finish it off? Well, this actually gets finished off with a homework exercise, which is this map pi1 from x cross y to y is a closed map. So if it's a closed map, it takes closed sets to closed sets. But that means that the image of this thing right here, this behemoth right here, which is closed, under our pi1 is closed. But that means that x minus the pre-image of v is closed. But if x minus the pre-image of v is closed, then that means the pre-image of v is an open set. But that's exactly where we're going to end up for f to be a continuous function. Okay, so now this theorem is sorted, and I'm going to leave you with some exercises. All right, now I've got two exercises for you. So the first is to show that if y is compact and c is a closed subset of x cross y, then pi1 of c is closed inside of x, where that pi1 is the projection map that we talked about in the previous theorem. Next, let's show from scratch, without the result that we proved in this video, that the closed interval from 0 to 1 is not compact in the real numbers with the lower limit topology. Now I say without the result of the video, what I mean by that is you can't just say, well, 0, 1 is uncountable and only countable sets are possibly compact in this setting. So you can't do that, but you can maybe mimic parts of the proof, and that's a good place to stop.